Number 85 from solving from June 2020. Let G be a finite group and we have to find which of the following are true. So let's check option 1. So if G belongs to G and has order M, and if n is greater than equal to 1 divides M, so G has a subgroup of order n. So we have this, right? Then the order of G is M, not the capital G, it will be small g. Order of G is M, and n vertical bar n is a factor of M, it is equation 1, and we have OG is a factor of O of the capital G. So this is equation 2. So from 1 and 2 we can get that n vertical bar OG is nothing but this G has element of order n. Right? It is element of order n. Since G is finite, so then G has a cyclic subgroup of order n, as G is finite. So in our case the option 1 is correct. So let's check with the option 2, that it is saying that if for any two subgroups A and B of G, either A is a proper subset of B or B is a proper subset of A, then G is cyclic. So we know that G is finite and order of G is n, since it is finite. Now if n is a prime number, then G is equivalent to Z of n. I can write it as Z of P, and this 0 is a subset of ZP, then G is cyclic, right? So if we consider that n is a prime number, now if the order of G is something like P to the power m, then G will be equivalent to ZPM, where G is cyclic, right? Now if order of G is a product of two numbers, suppose P and Q, possible elements of order will be 1, P, Q and PQ. These are the possible elements of order. So here you can say that A is a proper subset of B, or B is a proper subset of A, which is not possible. So in all other cases, this is not achievable, or it is not possible. This A is a proper subset of B, or B is a proper subset of A. So hence our option 2 is incorrect. Now option 3 is G is cyclic. Then for any of two subgroups A and B of G, either A is a proper subset of B, or B is a proper subset of A. Okay, so option 3, let's check the option 3 where these two are wrong. So if G is cyclic, so if we write that if G is Z6, then A we can write it as, will be 0 to 4 simply, and the elements are, so it is written as 2, and B we can write that 0 comma 3, which is okay. So G is cyclic, G is cyclic, but A is not a superset of B, neither B is a superset of A. So in our case the option 3 is also incorrect. Let's check with the last option, that is option 4. But it is mentioned over here that if for every positive integer m dividing mod G, so G has a subgroup of order m, then G is abelian. Okay. So if we write, if this we consider that G is a cross of Z2 cross S3, then order of G is equal to 12, and divisors of 12, what are the divisors of 12? You can find the 1, 2, 3, 4, 5 is not there, 6, 7, 8, 9, 10, 11, 12 is another divisor of 12. So G has a subgroup of order m, but G is not abelian in this case. Is a subgroup of order m, but G is not abelian. So in our case the option 4 is also incorrect. So we have only the G has a cyclic group of order m. So option 1 is correct option for this question. Question 87. So consider the polynomial fx is equal to this x square plus 3x minus 1. This is a polynomial. Which of the following statements are true? So if we can find the roots of this, so if you find the roots, so it will be equal to 0. From there we can get x is equal to minus 3 plus minus 9 plus 4 will be there by 2. So the roots will be minus 3 by 2 plus minus root over 13 by 2. So minus 3 by 2 plus root 13 by 2, one of the root, and minus 3 by 2 minus 13 by root 13 by 2 is the another. So let's check with this. So in the option 1 it is given that f is irreducible in z of this root 13. So we can write it as, we have to find whether is f is irreducible or irreducible. So z of root 13. So here we can write it as a plus b root 13, where a and b is both an element belongs to the z. So here the roots are x equal to a plus b root 13, a equal to minus 3 by 2 and b equal to half. So this doesn't belong, is not an element of z. So f is irreducible, we can say, in z13 root 13. Okay, so option 1 is correct. So f is reducible over q, set of rational numbers. Okay, let us check this. So option 2. So roots of f are, what are the roots? Are x equal to, we know that, minus 3 by 2 plus minus root over 13 by 2, right? And root 13 is not a rational number, we know it's not belongs to the set of q. So f is irreducible in q. Right. Now option 3, f is reducible over the q root 13. Okay, let's check with option 3. So q of root 13, so we can write it in this form: a plus b root 13, where we're considering that a and b both are elements of this q. Here the roots are, what are the roots? Similarly we can write that x is equal to a plus b root 13, where a is equal to minus 3 by 2 and b is equal to half, right? And it belongs, it's an element of q. So f is reducible, f can be reducible in this group, so reducible over q of 13. So our option 3 is also correct. Over q 13. Now we have to find the last option, whether this root 13, z of root 13 is a unique factorization domain, that is UFD. Okay. So option number 4. So if we write 1 plus root 13 whole square, right, so it will be simply 2 common 7 plus root 13, right? So 2 is irreducible, in Z13, okay, but does not divide. It is reducible, is irreducible in Z13. Let's write Z13, okay. Now we have to find whether it doesn't divide 1 plus root 13, right? So we can see that the z of this factor is not a UFD, unique factorization domain, right? So option 4 is incorrect, or we can simply use this example, this so we can write that. We can also do in this manner, that minus 12 is equal to minus 4 into 3. So if I do this, we can write it in this manner, that 1 minus root 13 multiplied by 1 plus root 13, right? We can also write it. So this, it is not an unique factorization domain, z of root 13, so it can be simplified. So option 4 is incorrect in our case, it's not a correct option. So option 1 to 3, these three are the correct options.